If I told you that after cremation, part of your body could drift across an ocean within weeks, join a cloud, and fall as rain in a completely unfamiliar place, it might sound like science fiction, yet physically speaking, that description is remarkably accurate. The real question is not, how do we disappear? It is, where does each molecule go? And during those 2 hours inside a chamber heated to nearly 1. Comme de so. What actually happens at the atomic level? To answer that, we have to stop seeing the body as a person and start seeing it as a collection of water, carbon, and minerals. It sounds clinical, but that perspective reveals a surprisingly expansive picture. An adult human body is about 60% water. If you weigh 65 kilograms, roughly 39 kilograms, of that is water close to 41-liter bottles. When the temperature inside the chamber rises to around 900-1 Congress, water does not hesitate. At Osutaje. Water boils. At Unu. Homdels. Vaporization is nearly instantaneous. H2O molecules detach from tissue structures, shift into gaseous form, and mix with the circulating hot air inside the chamber. Imagine placing a drop of water on a red-hot pan. It vanishes in an instant. Now multiply that by tens of liters contained within a body. The entire liquid component leaves the physical structure in a very short time. But water is only the beginning. The real story lies in carbon, the element that forms muscles, skin, organs, even DNA. Soft tissues are largely composed of organic compounds rich in carbon. At high temperature and in the presence of oxygen, carbon does not burn with visible flames like a log in a fireplace. It undergoes chemical reaction. Carbon combines with oxygen to form CO2. Hydrogen forms water vapor. Complex molecules such as proteins and lipids first break apart into simpler structures before being fully oxidized. If you have ever learned about methane combustion in chemistry class, this is a more complex version of the same principle. No magic, no disappearance, just the reorganization of atomic bonds. Within roughly 2 hours, most soft tissue transitions from solid form into gas. These gases pass through filtration systems before being released into the environment. Carbon dioxide molecules that were once part of your muscle fibers enter the atmosphere, where plants may absorb them again through photosynthesis. It resembles the biological cycle, only accelerated. Instead of waiting decades for natural decomposition in soil, the transformation occurs within an afternoon. Once the organic portion completes its transition, what remains is bone mineral. Bones contain significant amounts of calcium phosphate. This inorganic material does not combust at cremation temperatures. Rather than becoming gas, it is heated intensely, loses its organic collagen matrix, and becomes brittle. After the process concludes, the remaining white-gray bone fragments are mechanically processed into fine granules. On average, an adult body leaves behind about 3 to 3 kilograms of solid material. If you have ever carried a 2-kilogram bag of rice, you know it is not something that simply blows away. Notice the contrast. The original body mass may have been 70 kilograms. Only a few kilograms remain. More than 90% has transitioned into gas, not destroyed, simply transformed. So where are those molecules now? Some may be drifting in the atmosphere. Some may dissolve into ocean water. Others may already be incorporated into the leaf of a plant outside your window. It may sound poetic, but it is basic physics. Matter is neither created nor destroyed. It only changes form. In traditional burial, microorganisms and time gradually break down the body over many years. Cremation is simply an accelerated version of that same transformation. Instead of bacteria performing the breakdown, high temperature fulfills that role. This perspective does not make the story colder. If anything, it expands it. Our bodies are made of atoms that have existed for billions of years. The carbon in you may have formed in ancient stars. The oxygen in you once moved through primordial oceans. During cremation, those atoms do not vanish. They leave a familiar structure, and continue their journey within Earth's material cycles. There is a certain calm in that realization, not disappearance, but transition, not a full stop, but a comma in a much larger cycle. Viewed this way, the question, where do we go, becomes less frightening. Perhaps we simply return to where we once belonged a little faster, a little more efficiently, assisted by technology. And if tracing the path of molecules intrigues you, next time we could follow the journey of a single carbon atom from an ancient star to your lunch. It sounds improbable, but science often begins with questions that sound exactly like that.